If you strike a vibrating beryllium ion with rapid, continuous laser pulses, constantly checking its state, it freezes midair. This is the quantum Zeno effect. A quantum particle evolves smoothly over time, but rapid, repeated measurements force the wave to snap back to its starting point, locking an unstable particle in its initial state. In 1989, researchers at NIST proved this in a laboratory, demonstrating that the more frequently they interrogated a system, the more they suppressed its physical evolution. These results confirm that the measurement problem is a physical reality. Unobserved matter and observed matter follow two different sets of behaviors. The Schrödinger equation describes an isolated quantum system as a wave that evolves continuously and predictably over time. But the moment a measurement occurs, the Born rule replaces that wave with a single localized point, the specific outcome we observe in the lab. These two mathematical rules describe the same universe, yet they are logically incompatible. One is smooth and deterministic, the other is abrupt and random. This forces physics to ask what actually triggers that transition. The math does not define what qualifies as a measurement, leaving a gap in our understanding of how a single outcome emerges from quantum possibilities. Erwin Schrödinger proposed his famous cat specifically to mock the implications of this theory. He wanted to show applying quantum rules to macroscopic objects leads to a logical dead end. In his scenario, a single radioactive atom is linked to a mechanical trigger. If the atom decays, a Geiger counter detects the radiation and releases a lethal poison. If the unobserved atom exists in a superposition of decayed and not decayed, the mechanical system would force the cat into simultaneous states of life and death. According to the Copenhagen interpretation, this dual state remains mathematically real as long as the box is unobserved. Scaling the quantum rules to a human-sized object creates a reality that contradicts our daily experience, suggesting the core theory is missing a physical mechanism for large-scale systems. Part of the answer lies in redefining observation. In physics, a measurement does not require a conscious eye or a brain. It only requires interaction. Through environmental decoherence, a quantum system is bombarded by stray particles, like air molecules or light. These random interactions instantly flatten a fragile superposition. Because large objects are in constant contact with their surroundings, the environment acts as a persistent measuring device, preventing a cat from maintaining a dual state. While decoherence explains how a stable world emerges, it still doesn't explain why one specific reality is chosen over another. The underlying mystery of the collapse remains. Eugene Wigmore took this problem even further, imagining a scenario where the observer becomes the subject of the experiment. He imagined a colleague, his friend, isolated inside a laboratory. The friend measures a quantum particle and records a single, definite result. To the friend inside the lab, reality has resolved into one state. But for Wigmore, standing outside the isolated room, the entire lab, including the friend, exists as an overlapping wave of all possible outcomes. Quantum mechanics allows these two different, fully valid realities to exist for different observers, which challenges the idea of a single, shared, objective universe. Today, physicists remain divided. Ontological theories, like the many worlds interpretation, argue the wave function is a physical reality that literally branches into new universes for every outcome. Epistemic theories, like cubism, argue the wave function isn't a physical thing at all, but rather internal code representing an observer's personal knowledge. Despite decades of research, there is still no consensus on which of these perspectives is correct. The measurement problem suggests that the act of looking at the universe rewrites its rules, leaving the true nature of reality as one of the most significant open questions in physics.